So multipole expansion is just an alternate way of stating what we just did. So we just came up with the mathematical theory behind what's called a multipole expansion, which is to say that imagine that there's some thing here, r theta phi. We can't do phi yet because we didn't derive that part. It's not that bad. So it's actually easier than r, which is why it's for you guys on the homework, and I'm comfortable with, you guys all getting the right answer. So you give me a charge distribution. I know that it's going to create some electrostatic potential out in space. And the idea of doing this by representing it, not just like staring at rho and then magically coming up with whatever V is, that might be really hard. The idea of doing it systematically through the correct functions for this coordinate system, which is to say we just keep picking apart what, the L equals 0 term is, the L equals 1 term, and we know that they look like this. Except that this closed parenthesis shouldn't be there. And then these goofy things that we'll spend a little bit more time talking about, of course, because they're kind of new. The idea of doing this sequentially term by term by term by term is what's called a multipole expansion. And in fact, if you think about it, the L equals 0 term, like if you concentrate on this, the L equals 0 term is something that right? So this is the potential for a point charge. And then the L equals 2 term, if you remember what a dipole looks like a dipole. And then the L equals 3 term will be a quadrupole and an octupole. And I don't know what 16 is in, I guess that would be Greek. But this is the idea of a multiple expansion, is these correspond to different types of charge distributions. Okay, so this is what we're kind of doing. Okay, let's first do something that you can't always do. I think we talked about when each of these terms contribute, but let's consider a localized lump of charge, which is to say all the charge is here. What can you tell me about these terms? Just say look really far away from this localized lump of charge.
If we're pretty far away, then the A terms are going to be large and the B terms are going to be pretty small.
Yeah, in fact, specifically, if you go towards infinity, what would happen to all of these terms?
I think the B terms would vanish and the A terms would diverge.
Yeah, so if I have, I don't care how complicated and funky shaped it is. If I get like really, really, really far away from a localized charge, it's going to essentially look like a point charge, right? And so I really want its potential to go to 0. So if I have a localized charge distribution, we could have infinite planes and things like that later on in our life. But for a localized lump, all of the terms where this actually is not a constant, they've got to be 0, because otherwise they're going to blow up. So for localized charge distributions, we're going to have V of, now we're really just talking about r theta. We haven't included the azimuthal terms yet, but know that they exist. We can have an A naught. So if you have a potential, because the potential essentially has an integration constant, that's what this is. A naught is an integration constant, and it's fine. You can leave it in there. It shouldn't correspond to anything physical, because when you take the gradient of this to get the electric field, which does have to do with physical stuff, it's going to go away. So that's the only A term that can remain, because the rest would blow up at infinity, and we don't like that. So BA PL r to the L plus 1 times PL cosine of theta. Okay. So this is the multipole expansion for a localized lump of stuff. Let's look explicitly at the first couple of terms. And you'll recognize them even from 1220? Okay, so don't worry about the A naught. Again, it's just like an integration constant. And when we do find E is equal to minus grad V, it's gone anyway, so who cares? So L equals 0, I get B0 over R. And then what I would do is I would look up the table of Legendre polynomials. Everywhere I see X, I would plug in cosine of theta. The 0th Legendre polynomial is just a constant, so that's just times 1. So this is saying that if I just had an L0 term, I could, in general, I'm going to have to sum up all of them. My potential R theta is just some constant over R. What is the potential of a point charge? Well, that's K Q over R. So this is right. So this is what's called the monopole term. And B naught over K would tell me the total charge enclosed in the thing. Okay, let's look at the L equals 1 term. So the L equals, just the L equals 1 term, in general, we've got to add them all up to get some arbitrary potential. So that's B1 over R to the 1 plus 1 to power. And then I would look up the L equals 1 Legendre polynomial, that's X. And then instead of X, I would say cosine of theta. This is what's called the dipole term. Go back in your E&M textbook, or even Giancali or whatever you used for intro physics. At some point in there, the field and the potential of a dipole, which is plus Q minus Q, separated by some distance d, is determined, and it looks like this. So this really is a dipole. The interesting thing about a dipole is it's got no net charge. So the net charge, even of this complicated lump of stuff, can be completely determined by and to the dipole or the monopole term. Okay, we'll do one more because the Legendre polynomials are goofy. So let me get rid of our poor crappy board work, but whatever, not a board. So the L equals 2 term, just the L equals 2 term, that would be B2 over R cubed. And then I would look up the second Legendre polynomial, so P2, and then I would, and that's a little bit nastier. Make sure I get the right convention. So that would be 1/2 3x squared minus 1 to 1/2 times 3 cosine squared theta minus 1. And this is what's called the quadrupole term. If I wanted to sketch a quadrupole, what do you suppose I would sketch?
Like 4 point charges.
Yeah, dipole is 2 monopoles, quadrupole is 2 dipoles, and octupole, which is the next term, is 2 quadrupoles. So this would be like plus Q minus Q plus Q minus Q. And then you keep going. Okay, so we'll do one example of, again, I think the theory, when I first learned it, it was like kind of off-putting. I'm like, this seemed like the floor just dropped out from underneath me. But this is the way it usually works, is that it makes your life much easier. Because again, the idea of somebody specifying some like really gross function for a charge distribution, and then you just trying to work that, work out what the solution is through the differential equation without any systematic approach of breaking it up would be really tough. So the way that this is going to work in practice is the charge distribution will have a multipole expansion, and you just like connect the, plug this multipole term into that multipole term. But any questions about that before we do a quick example? Okay, so this is the payoff after all the Gram-Schmidt and all the orthogonal polynomials. We'll talk a lot about orthogonal polynomials. This is probably the first time. Sphere. I think the only thing that's squirrely about this is a uniform electric field would kind of make you immediately think like, aha, I want to use rectangular coordinates. But the metal sphere itself is going to have a spherical polar distribution on its surface, and that's what we want to find. So we have an external field. E is equal to E naught K hat or Z, whatever you want to call it. So, at the far edges, but then we're just plopping a metal sphere into it. And the way that this might look is as follows. Got a sphere, use a sphere. Here's my charge sphere. Ta-da. And I think okay, so I have a metal sphere in an external electric field. Really far away from the sphere, the electric field is going to be completely unperturbed. But then what's going to happen is closer to the sphere, charge distribution is going to build up on the surface of the sphere, and that's going to make some interesting looking field lines. And because the sphere itself is uncharged, if I, in my cartoon, draw 5 pluses on this side, I got to put 5 pluses on, or 5 minuses on that side. And then let's just say that this has some radius r. Okay, so really far away, this is E equals E naught K hat. So just positive Z direction. Okay, so what do I know about anything to do with the potential? So I'm trying to find the potential. What must be true about the potential on the surface of the sphere? So you can think about potential as kind of like being uphill and downhill for the charges. So if a charge is at 2 volts and right next to it is 1 volt, what's the charge going to want to do? Positive charge. It's going to want to run downhill towards the 1 volt. So if I have a metal sphere, so perfect conductor, and I had some higher region of voltage and a lower region of voltage, what would all the charges want to do? So what I'm getting at is we have two things that we know about this. On the surface of the sphere, what's true about the voltage? In fact, in some sense, this is kind of the definition of what a perfect conductor is a perfect conductor just moves voltage around until the voltage on the surface of the perfect conductor is constant. If there was a region of higher voltage charges, which are free to just kind of pop out of the ether on a metal sphere, would go from that high region of voltage to a low region of voltage. They would run downhill, like water going down a surface. I don't see why not. Let's just say that if the surface of the sphere is constant, let's just call that constant 0. And then 2, this is the little bit more obscure one, is that really, really, really far away from the charge. So as V goes towards, or as we go towards infinity, this looks like a parallel plate capacitor, right? With like constant field lines if we're really far away from the charge. So the asymptotic behavior looks like this. So that, if we were in an E&M class, I would hassle you guys for about 5 minutes about that until you figured it out yourselves. But we have 3 minutes left, so because I want to show you GitHub. So I'll just say an E&M argument says that this is what the voltage should look like far from the sphere. And I'm going to go a little bit farther and say that, what Z is? Z is R cosine theta. Because ultimately what we want is this expressed as R and phi, because we want to map on what we want to do is we want to find the multipole expansion. And the multipole expansion of V R theta is equal to, in general, so we don't have a localized lump of charge. We've obviously got some charge making the external field. So we can't immediately just throw away terms. We'll have to argue that, most of them go away. AL RL plus BL over RL plus 1 plus this weird Legendre polynomial stuff, right? That's always true for something that's azimuthally symmetric. So I rotate the sphere and it looks the same. So now the question is, which one of these remain? Well, I know that really far away from the sphere at infinity, I just have this term. So that means the only A term that can remain is the one that gives me this. And I know that what's true on the surface of the sphere is at the surface of the sphere, I have a constant potential. You get to choose what the constant is because it gets removed by a derivative anyway when you look for the electric field, which is actually the physical thing. So what we have is 1 tells us that when we look on the sphere itself, so on the surface of the sphere, capital R, we have 0, right? And so this vanishes term by term. So the Legendre polynomials aren't going to vanish. We're going to be able to move around theta. But what must be true is that each individual AL capital RL plus BL capital RL plus 1 has got to be equal to 0 for all L. Yikes. And so what that means is BL is equal to minus AL shuffling and solving R to the 2L plus 1. Right, so we used to have 2 times infinity coefficients. We figured out infinity of them. We just need infinity more. That's really nice. And then the second thing, so plugging that in, now we know that VR and theta is equal to some L goes from 0 to infinity. AL, plugging in our condition for BL, RL plus R2L plus 1 over L plus 1 PL cosine of theta. Okay, the second thing we know is that really far away, all we have left is a cosine theta term. And we know that P1 cosine theta is cosine theta. And then we have this constant term, P0 of cosine theta is equal to constant, namely 1. So those are the only two terms that we have. Everything else would have higher powers of cosine. So got a little bit crowded, so let me erase. So from the, whoops. From the condition that the potential is constant, namely that constant is 0 at the surface, we got this. And then the second condition, which I just erased, is that far away, not at the surface, but far away, we have R cosine theta plus 1. What we're left with is that only A1 and A0 can exist. So A2, for instance, would have to be equal to 0, and then, you know, all the way up to A infinity. So the higher order terms need to vanish. And then plugging them in, what I would get is that A1 would be equal to negative E0 from the condition that I erased, the fact that the potential needs to be R E0 Z, and A0 is equal to some constant. Again, it's going to derivative away. You can choose it to be 0. Why not choose it to be 0? And therefore, plugging all of that stuff in, a little bit cramped, because we have, yeah, right at the end of class, E0 R cubed for R squared cosine theta. So that is the potential for the sphere immersed in an external electric field. So you can show that it's got no monopole term because it's got no net charge. It's really just a fancy dipole with the external field. But the way that this was done was writing down the external conditions just based on our understanding of how conductors work. And then because we know that this is always the solution, in the same way that you know that a Fourier series is always just a collection of sines and cosines, we were able to match that directly onto the solution. Okay, so we'll do GitHub stuff and Markdown on Thursday. So that got a little bit longer than I thought. and talk a little bit more about completeness and some of the recursion formulas, Rodriguez's formula, so things that you can do with the Legendre polynomials. And then what you guys will do is add the third piece of the puzzle, the third part of the separable equation, so the azimuthal part, which turns out to be really easy. Don't freak out. They're really nice. The axial part is the worst part of the Laplacian and spherical polar coordinates. Right. I will stay if people have questions. Otherwise, I will see you guys on Thursday.
Awesome. Thanks.